Okay, it's almost, we are almost there. In 2 minutes, I'll open up. Okay, it's on live, going live now in Facebook also. Okay. And you can see my my screen, that Healthy Climate Initiative, that PowerPoint, right? Or is it stopped? Okay, I'm going live. Okay, so we'll have I think the attendees are joining, so. Good morning, good afternoon, and good evening, depending on where you are. My name is Soumitra Das. I'm the president of Healthy Climate Initiative. Let us give a couple of more minutes. I see the people are still joining. So we'll start sharp at 11:03 in 2 minutes, 11:03 my time in United States, East Coast time. And we'll go from there. Thank you. So let us start. Again, my name is Soumitra Das. I'm the president of Healthy Climate Initiative. Before I introduce Dr. Peter Wadhams, let me introduce the agenda and say a few words about Healthy Climate Initiative. Today's agenda is the following. After the introduction, we'll present a short film, Kolkata 2050, made by Discovery Channel. It will show the impact, climate change impacts on Kolkata, and the people of the city are going to face, likely to face, in the not too distant future. The film will be followed by the Need for Carbon Dioxide Removal webinar by our speaker, Dr. Peter Wadhams. This will be followed by question and answer. You can submit your questions in writing, and that will go for 15 minutes. But we'll not strictly adhere to that 15 minutes. If we have more interesting questions, we'll go over time if we want. And then we'll conclude with a vote of thanks. Briefly about Healthy Climate Initiative. It's a nonprofit education and advocacy group to combat climate change. Our mission is to restore climate and make it safe and healthy for future generations. We have undertaken several activities, but I want to highlight our internship program. We recruit interns, summer interns, from high schools and colleges to work on climate change related projects. The goal of this program is to create youth leaders of climate change. Currently, we have 7 interns from India and USA working on climate related projects under my guidance and a professor from New York University. We plan to expand this program on a larger scale next year. For more information, please visit hci.in.net. And if you are interested to become a member and be active in HCI activities, please contact Mr. Chandan Bhattacharya at ckbhattacharya1963@gmail.com. Now I have the honor of introducing Dr. Peter Wadhams. Dr. Wadhams is a professor of ocean physics and a head of the Polar Ocean Physics group in the Department of Applied Mathematics and Theoretical Physics, University of Cambridge. He is the UK's most experienced sea ice scientist with 40 years of research in sea ice and ocean processes in the Arctic and the Antarctic. He has led 46 research expeditions to the polar seas and carried out 6 voyages to the North Pole from 1971 to 2007. He was a pioneer in the use of autonomous underwater vehicles under sea ice. Next, we are going to go and watch the film, and this will dovetail well actually with Dr. Wadhams. So let us watch the film. Just give me a second. Just give me a second, sorry about that. So that's the film they wanted to show. This is not just an example. Kolkata is an example. The same future is going to happen 570 coastal cities in the world. Now we'll hear from Dr. Wadhams. Let's again. Okay. Peter, you can take over. Peter. Can Peter unmute yourself, Peter? Yes, okay. Peter, you need to unmute yourself. Peter?
Okay, how's that?
Okay. Okay, go ahead. Thank you, Peter.
Okay, pleasure. Well, thank you very much for inviting me to give this talk. And so what I want to talk about really are two things, the main one being the topic, of course, which is the need for carbon dioxide removal if we're going to save ourselves from the sort of terrible effects which climate change is bringing to us. But I'll start by talking about some of the immediate and present effects of climate change, which of course include the flooding and the sea level rise dealt with so powerfully by this video that we've just seen. So I'm now trying to go to the next slide. Can I do that myself? It's okay, marvelous. I was pressing the wrong button. Right. Well, my talk is based to some extent on a couple of books that have come out, a book and a film that have come out recently. And the book is The Farewell to Ice, which really starts by explaining what has happened to the world in Arctic terms, in terms of the disappearance of ice. And then the following film. Okay. It still works. Just okay, thanks. No, okay. And the related to this is a movie which is just out last year called Ice on Fire, which was made by Leonardo DiCaprio and deals with all of these problems related to climate change and the problem of removing carbon dioxide from the atmosphere. And he deals with things which normally are not dealt with, like the problem of methane release from the Arctic. And so I have to get. So we start the story. We look at what's happened to the temperature of the world, and the lower map here shows the average temperature, global temperatures going back to the year 1000, and we know. We were able to measure those temperatures not because of thermometers being around, but because of ice cores and making measurements from dead trees. And so what it showed was that from the year 1000 until about 1800, the temperature of the planet was gradually decreasing. And this was expected because we are, in theory, on our way towards the next ice age, which is given by astronomical factors. So we know that an ice age will come in about 20,000 years. So we were slowly moving down towards that. And then suddenly in about the mid-19th century, as we see on the bottom map, suddenly the temperature started to rise very, very rapidly. A completely different rate from the slow cooling. So people wondered what has happened, and the answer is that it coincided with beginning of extensive use of fossil fuels. Before 19th century, we had an agricultural economy in the world, and then we started to mine coal and develop industry. And these set of graphs show what happened, that the levels of these gases in the atmosphere remained very, very stable right from the end of the last ice age for several thousand years. That's carbon dioxide, methane, and nitrous oxide. They remained very, very stable gases. And suddenly they all took off almost vertically from the scale here. And this was the enormous effect that mining coal and burning coal had upon the atmosphere of the Earth. Now, the explanation for this came in 1896. And so before then, we had an excuse for not knowing what was going on. But in 1896, Svante Arrhenius, who was a Swedish scientist, showed that the warming of the planet was due to the release of all of these gases into the atmosphere. The main one, which he identified, was carbon dioxide, which of course he calls carbonic acid, but with methane and nitrous oxide as lesser gases. So he concluded, and he calculated very well, that what was happening was that these gases, particularly carbon dioxide, were allowing shortwave radiation from the sun to reach the planet's surface, but taking away a lot of this longer wave radiation that the Earth was trying to emit back into space to balance the incoming radiation with the outgoing radiation and keep us at a steady temperature. This outward going radiation was being held back by absorption by CO2. And he calculated how much it was being held back, and his calculations were quite accurate. The trouble was that he thought there was nothing much to worry about because all of this extra CO2 would be dissolved in the ocean. And he thought the ocean had an infinite capacity for storing CO2. So we needn't worry about this effect, even though it was going to be causing an increase in CO2 levels, both in the atmosphere and in the ocean. And we know now that this big burst of carbon dioxide emissions that came about when we started to mine coal and burn it has continued, and it's got steadily worse. We didn't bother to measure it until 1958, amazingly, when a measurement system was established on the top of Mauna Loa, the volcano in Hawaii, and regular measurements taken of carbon dioxide levels and other gases. And we found that the carbon dioxide level was increasing and in fact was accelerating. It's exponentially increasing, that the rate of CO2 increase keeps on going up. 280 was the level at the end of the Ice Age, and the natural level that the Earth would like to have during a warm period, 280 parts per million, but it was already at 320 in 1960, and now it's today that it's 411, and it goes up by about 3 parts per million every year, and this is a very serious effect because scientists have calculated that if we have a level much above 350, then we're bound to have a warming of at least 2 degrees globally because of the extra heat held back by the carbon dioxide. So 350 is a danger level, and we've gone way past that, and we're increasing our CO2 in an accelerated fashion. And why is this happening, and what can we do about it? Well, why it's happening is because China and to a lesser extent India are both increasing their carbon dioxide emissions by very, very rapidly, while the USA and Europe are decreasing theirs slightly. But that's mainly because, not because we're particularly virtuous, but because we've transferred a lot of our industry to China. So China takes up the slack and the small decrease in Europe is offset by a large increase in China. You'll see that the graph also talks about cement, and cement is the really most villainous substance on the planet, because the production of cement uses a lot of energy, and the chemical process by which cement is produced also emits carbon dioxide. So cement production is a particularly serious form of carbon dioxide pollution. And it's very unfortunate that most countries in the world seem to be increasing their cement production. The world would do a lot better if we didn't build so many concrete buildings. Next slide. So that's what's happening. Now, what does that do to the world? Well, we look first at one of the obvious effects, which is that if the climate is warming, then somewhere or other, wherever there's ice, it will start to melt and turn into water. So we look first at the Arctic, and we can see that in the past, this is back in 1970, the right-hand picture shows the typical situation in the winter, where the whole of the Arctic Ocean is covered with ice. That's the light blue color, and a lot else besides. And in the summer, much of that ice melts, but there's a big area of ice that takes up the whole of the central part of the Arctic basin. This was the way things were. So you couldn't actually walk across, you couldn't sail across the Arctic or anything like that. It was ice covered winter and summer, just a little bit more in the winter. But that immediately started changing as soon as global warming took effect. And we now have a big retreat of the ice in the summer, so that it's lying well back from the coastlines of the Arctic. And today we're able to sail right across the Arctic or around the edges of the Arctic at will. And there's now trade routes in the Northern Sea Route and the Northwest Passage. The ice area in summer is going down in a linear fashion, and we can see it's steadily decreasing. And the ice itself is changing its state, it's changing its properties. This is the way the ice used to look when I was young and used to go to the Arctic. Very, very thick, heavy, many meters thick, difficult to walk on, difficult to break through with a ship, even a powerful icebreaker. It was a really formidable barrier. Now today, most of the ice is less than a year old. It's very thin, and these are some Inuit hunters in the winter in northwest Greenland, but that ice that they're on is very thin, and their sledges often go through the ice. So in fact, as part of a European project, we helped them by installing radar on the bottom of their sledges to give them a warning of how thick the ice was that they were working on. Another thing is that the ice, even in winter, is now broken up into a huge mass of channels called leads. This is half the Arctic Ocean shown here from a satellite picture. And the blue here is open leads, open water, and therefore it means that you can't easily travel over this ice. We used to do our research by landing on the ice with an aircraft and setting up camps, but you can't do that anymore with all this water around. So we know that the ice is decreasing in area. We can see that easily from satellites, but we also need a means of knowing whether the ice is getting thinner. And you can't tell that from a satellite. You have to actually go and measure the thickness, in fact, from underneath. So I've done several voyages to the Arctic in submarines where we've had helpful support from the Royal Navy, where you go underneath the ice with an upward-looking echo sounder, which measures the distance from the submarine to the ice and tells you how thick the ice is. So this shows where we would mount that sonar on the submarine and the kind of record we get from being underneath it. Now, we can therefore combine the thickness measurements done from the submarine with the area measurements done from the satellite, and that tells us the volume, the actual amount of ice there is in the Arctic. And we see this data for summer going from 1979 until a few years ago, shows that the volume of ice is only about a quarter of what it was 20 years ago. So there's 3/4 of the ice in the Arctic has gone. So let's look now at what that means for sea levels. It's relevant to the movie that we saw. That the warmer atmosphere that we now have in the Arctic, especially in summer, because there isn't ice there anymore. So the air warms up because it's not being kept cool by a layer of ice. So this gives us an anomalous temperature. Here we see it's showing that the anomaly relative to 1970 was about 11 degrees in the middle of, that's 11 degrees Fahrenheit, in the middle of the Arctic Ocean. And we can see when we look at Greenland, here for instance, on the right, that the Greenland ice sheet is now subject to warming due to the fact that the whole of the Arctic is warmed up. Now, this is complicated by the fact that the whole of the Arctic is warming up faster, in fact, than any other part of the planet. So it's about 3 or 4 times as rapid a warming in that high Arctic as you get in the rest of the planet. So what does that do to Greenland? In the past, up until the 1980s, the Greenland ice sheet remained frozen year-round because it's at a high elevation. It's about 3,000 meters above sea level. So the temperature is well below zero, even in the summer. So in the past, you would have a little bit of melt of Greenland round the edges at sea level, like the left-hand picture. And that would be all you'd get. And then that ice would refreeze again in the winter. What we get now, though, is what we have on the right, which is almost the entire ice sheet is now melting in the summer. So you've got meltwater over the entire surface. That meltwater runs away down through waterfalls, streams, holes in the ice, out to the ocean. And when it gets to the ocean, it raises sea level. So what used to be a minor source of water for raising sea level is now the major source. In the past, seawater gets less dense as it gets warmer. And so all over the world, sea levels were gradually rising because the ocean was gradually getting warmer and expanding. Now that process is accelerating because the warmer water is being joined by new water that's being dumped in the ocean from the Greenland ice sheet and also now from the Antarctic ice sheet. So we've got a way of measuring that now by a satellite called GRACE, the Global Gravity Satellite, which actually measures the mass of stuff underneath it. So when the satellite passes over the Greenland ice sheet, it shows a change in mass, and that tells us how much ice there is in the Greenland ice sheet, and we can see that mass is decreasing, and the red is the long-term decrease, the blue is the annual decrease, and we see it's now losing about 300 cubic kilometers a year. All that water is going into the ocean and causing a rise in sea level. And I had the opportunity to see this going on. I've worked in Greenland quite a lot, but last summer I was up there on August the 1st and on the ice sheet. And August the 1st happened to be the day when the largest single day's loss of ice happened from the Greenland ice sheet. It was 12.5 billion tons of ice. And the main reason was it was a very warm day, 21 degrees C, which you don't expect on top of an ice sheet that's 10,000 feet above sea level. So this is what the ice looks like. We can see that it's getting dirty because the ice is melting, leaving a lot of dirt behind. But now this is a closer up view of the top of the ice sheet, and we see that it really does look dirty. This is called black ice. And the reason we can see that is that the ice sheet, which used to be beautifully white, of course, covered with fresh snow every year, this ice sheet would reflect nearly all the radiation falling on it, at least 90% of the way. Now, as it melts in the summer, the water percolates away, but the ice, the dirt that was part of the ice sheet that had been dumped on the ice sheet over hundreds of years of blowing dust and dirt, that actually stays behind. It sinks downwards because the water has gone, and gets darker and darker because it's getting denser and denser with dirt. So we're getting now this color of dark brown or black, and it's not even slippery anymore. You don't slide on this because there's so much mud. And the darkness of this means that the ice is now reflecting much less radiation than it did. So the black ice causes a speeding up of the melt of the ice sheet because the ice is losing, is darker than and absorbing more radiation than it did in the past. So this speeds up the Greenland ice sheet melt in a way that wasn't expected by scientists. This is just another view of the edge of the ice sheet. You see how thick this dirt layer is. You can only scarcely see the ice underneath it. And then we see one of these raging torrents of meltwater, which is taking the ice melt out to sea and causing sea level to rise. This whole process is now beginning in the Antarctic as well. So the predictions of how much global sea level rise we're going to have been changing very, very rapidly. The blue line here is the observations of sea level rise in the past up until the year 2000. And we can see it was a fairly gentle process, about 20 centimeters in 200 years. But each time we do measurements now, the estimates go up. So 2007 was Intergovernmental Panel on Climate Change. It's now gone up from their estimate of 20 centimeters up to at least a meter, and most scientists think it will go much higher. This is the amount of sea level rise we'll get by the end of the century. So it's now a conservative view to get 1 or 1.2 meters, and most realistic scientists who are looking at these processes accelerating are expecting that there'll be much more than this, maybe 2 meters, even 3 or 4 meters, which is a catastrophic rise because the whole of the world's oceans are rising by that same amount. Now this has a very bad effect, and I'll explain this because it has an impact on on Calcutta and on the Bay of Bengal. Because if we look at a given point on the ocean, the height of that point varies with time. That's this bell-shaped curve here because of tidal changes, wind, temperature changes. There's any point anywhere in the ocean doesn't have exactly the same height. It varies through a range, and this varies through this bell-shaped curve. And we can see that if it's at a very high level, for instance, high tide combined with a wind blowing, generating more water flowing into an area, then there's a possibility, a small possibility, that there'll be a catastrophic flood. So the little area in here is the probability of a catastrophic flood, with this as the distribution of height of the sea surface. Now, supposing a few years go by and sea level rises because of all this ice from Greenland, and the distribution of heights now looks like this, the dotted line. You might think, oh, well, that's no big problem. We've only increased the sea level by this small amount. But in fact, the whole curve has gone up by that amount. So if we look down here, the probability of a catastrophic flood has gone up from this little bit here to this big bit here, is multiplied by 5 or 6 times. So if we have a small amount of sea level rise due to the addition of water from Greenland, we have a large increase in the possibility of having a disastrous flood. So when we're looking, for instance, at the Bay of Bengal, where we have sea level rise going on, we have quite frequent events where a southerly wind is blowing, is moving water in against the coast, then the probability of a catastrophe or a flood goes up now from this level to this level. And that means far more frequent floods along coastlines if they're unprotected. This assumes we've done nothing to add to the heights of our flood defences. If we keep them at the same height, the probability of a flood goes up. So a lot of the coastline of Bangladesh and India in the Bay of Bengal, it isn't possible to raise the heights of flood defences, or it's much too expensive because of the very the convoluted coastline, and the result is going to be much more frequent floods. And that's a really serious consequence. And just to mention a few more effects before I talk about what we might be able to do about it, there's an increased loss of snow now in the Northern Hemisphere. The brown here are areas which used to be snow covered in the Arctic, even in summer, and are now not. There's an increase, as we know, in fires. This is just an example of how random fires are now in the United States. This was last year. We were just driving along the freeway in the city of Pasadena. Suddenly we saw this huge amount of smoke, and it wasn't a burning building. It was a brush fire, and this brush fire was an area of brush and vegetation that was coming down in towards the city, and was enough to cause a fire inside the city of Pasadena, which is a very large and very urbanized city. Another effect is the possibility that we'll have a very large accident due to methane being released into the atmosphere. Now, the Arctic, as you can see, is an ocean which is very shallow around its edges. The light blue here is continental shelf, which is only 50 to 100 meters deep compared to 4,000 meters in the center. And when in the summer, when the ice now melts and goes away, which it didn't used to do, but now it does, then the areas around the edges of the Arctic warm up because you have shallow water, we have ice-free conditions, and that means that the water can warm up and we can get several degrees of warming. And when that happens, there's a protective layer at the moment on the seabed, that's the red layer here, which is permafrost that keeps the bottom frozen, and below it, all the deep, many hundreds of meters of sediments are made of methane, which is in solid form because it forms part of the sediments. But as soon as you take away this permafrost, which is happening very fast now, the methane gets released. It turns into a gas and comes up as a plume, which reaches the surface. And this is here only 60 meters deep. This is in the East Siberian Sea. And that methane getting into the air makes it into a very, very powerful greenhouse gas. It's much more powerful than carbon dioxide. So here's a mechanism by which methane is now in large quantities getting out into the atmosphere. This shows some methane bubbles rising, in this case, up against some ice. And when we start looking now at methane levels measured in the atmosphere, they used to be fairly stable, but now they're not. The red now here shows the last 3 or 4 years of growth, and it's started to accelerate. So methane is accelerating in the atmosphere, and it's largely due to methane coming out of the Arctic waters, the Arctic shallow coastal waters. A final effect I'll mention is the weather effects, which again we get all over the world now, including India, which is caused by this meandering of the jet stream. The jet stream is the wind that blows from west to east, which separates the polar air over the North Pole from tropical air. It used to be more or less a straight line, but now it's slowed down because the difference in temperature between tropical air and polar air has decreased. Polar air has warmed up. So we get now not a big change between polar air and tropical air. So the wind has less to drive it. And instead of being a straight line, it becomes this meandering line. And because of that meander, it allows you to have warm air going to places which are normally cold, and cold air coming down to places which are normally warm. So here, for instance, we see warm air in the central North America occurring right up to high latitudes, and we can see cold air along the eastern coast going down to low latitudes. So we get alternating extreme weather conditions of heat and cold. We've seen those in all over the world now. We're getting them in Europe, you get them in Asia as well, because the jet stream is a worldwide phenomenon. So this has a terrible effect in that it affects the production of crops. When we look at crop production, I think we see India here as a high producer of crops at a lower latitude, so it's fairly safe. But the latitudes that are unsafe are United States, Europe, Ukraine, Asia, and Northern Asia. Those are where the jet stream is having an impact and causing a change in the crop production, because when you have extreme heat, cold, and bad weather, you're affecting crop production. And this is already doing nasty things to our production of food. In the year 2000, the UN produced a food price index and set it at 100 to look at the average price of food all over the world. And by the year 2008, it had reached over 200. So food prices had more than doubled. And this coincided with big decreases in ice cover in the Arctic. Then it went down a bit, but then it comes up a bit, and it's again up above 200. We see from the place names here that these are places where the high price of food in cities in poorer countries makes for social unrest and great difficulty for people to be able to buy food. And this can only get worse because the climate impact on the weather impact will get worse, and that means the influence on crops will get worse. Also, the increase in warming would reduce the yield of many crops, and if it's been calculated, if we have warming of more than 2 degrees C, then the yield of nearly all the major crops that we eat, food crops, will go down: rice, wheat, maize, soybean. And this is something that is very serious, and so which is why the UN said we have to try to avoid a warming of more than 2 degrees. So what can we do about all this? It looks pretty nasty, and it is. So we can't, what everybody says is we have to reduce carbon emissions. That's this first line here. And it's the standard solution, which I don't think is a solution at all, that if we reduce carbon emissions, then we'll be reducing global warming. But we won't, because carbon dioxide stays in the atmosphere for at least 1,000 years. So when you add carbon dioxide to the atmosphere, it stays there. It doesn't go away. So it means that even if we reduce the rate of carbon emissions, we're still increasing the carbon dioxide level, which means we're still getting warming. So warming is still continuing. There's no way that we can actually bring the climate back to a livable level. So that's very, very serious. But people are finally beginning to realize this and realize that we can't solve our problem by reducing emissions, even if we reduce them down to almost zero, which can't be done anyway. We won't be able to save the climate or restore the climate. So the only way is actually to take carbon dioxide out of the atmosphere and reduce the CO2 level that way, get it back towards what it was before industrialization. So direct air capture is the simplest way. Find a way to scrub it out of the atmosphere, reduce the CO2 level. Next slide, please. And this was the message, of course, from Greta Thunberg, although she said we need to do very urgent emissions reduction. But of course, that's not enough. That's important, but it's not enough. Next slide, please. One way, what are the ways we can do this? Well, one is to actually try to reflect more energy back into space so that we reduce the greenhouse effect. And on the left slide, we see the idea of putting aerosols, that's tiny powdered particles into the upper atmosphere, and they'll then reflect energy back into space. Another way, which is this very nice picture here, invented by a Scottish engineer, is to pump, to have robot ships floating around, pumping up water, seawater, through these pipes up into the base of marine clouds. Marine clouds which take up more than half the ocean and have bases quite low down. The water particles get into the cloud and brighten the cloud. So with the cloud being brighter, it reflects more energy back into space. And they calculate that they could offset most or all global warming if they had enough of these ships. Because it doesn't actually deal with the carbon dioxide. And one of the things it doesn't deal with is the fact that carbon dioxide also dissolves in the ocean and is making the ocean more acidic, which will kill off marine life. It doesn't solve that problem at all. All it does is offset the actual warming. Next slide. Now, if we want to deal with the whole problem, we've got to actually get rid of the carbon dioxide. And the various ways to do this have been suggested, but I think generally we end up deciding it's the right-hand one is the one that's most easy and likely to be done, direct air capture. Other ones that have been suggested are, well, were the ones that were on the last slide. One was just reforestation, and reforestation means planting lots and lots of trees, which is in general a good idea, but it doesn't, it means that in the last slide, I showed you the area that you'd have to cover to be able to rid yourself of all of the global warming that was happening to the continent of Europe. And it turns out the area of forest you need is the same as the area of Europe. So you'd need to cover the Europe 100% with forest. A second method is called BECCS, which is biological carbon capture and sequestration. It means you grow a fast-growing biological material like waste, basically waste. You burn the waste and you capture the carbon dioxide from the waste. It seems a bit of a roundabout method, and in fact, again, it uses up a lot of land. And the final one, which doesn't use up a lot of land, is direct air capture. Oh, well, the third one, which I should have mentioned, is an idea to cover the surface of the Earth with a kind of powdered or ground up olivine rocks. Olivine rocks absorb carbon dioxide. So you can cover beaches, fields, everything with olivine rocks, and it will actually get rid of carbon dioxide. But firstly, very, very slowly. And secondly, once it's used up, you have to then go and spread some more. So it's not realistic. The realistic method is to pump air through some capturing mechanism, take out the carbon dioxide. And that's what DAC, or direct air capture, which is what most effort is going into at the moment. So the amounts involved are going to be huge. If we want to just take out the same amount as we put in, then we've got to take out 42 gigatons a year, which is 42 billion tons of carbon dioxide. That's what we put in every year. And if we want to bring the carbon dioxide level down towards pre-industrial level, we've got to take out more than 42. The 42 just compensates for what we're doing now, and then we need to take more than that. And so far, we could do that more easily if we actually did reduce our emissions, because then that would mean the amount we'd have to take out by this method would be less. But so far, there's been no evidence that we've reduced our emissions at all. These Mauna Loa data just show emissions going up. And so some of the DAC methods that have been developed and are going into larger scale production look very promising. One that's been developed in California at Los Gatos is a conversion of the carbon dioxide into limestone rock. Now, what you do is you have a whole series, you have hundreds of these things, blowers, which blow air over a bed of material, which includes a carbon dioxide absorber, which is usually a liquid. It can be an amine or sodium hydroxide. There's a number of simple chemicals which absorb carbon dioxide. Next. And it's captured by this solution. You then pass it through a series of equipment, depending on what you want to do with it, which takes the carbon dioxide away, and then you pump the solution back into the blower and to carry on the process. And the problem is that for this 42 billion tons, there's no problem there about taking it out of the atmosphere, because the chemistry of carbon dioxide removal is pretty simple. There's no, it's not you don't have to be a Nobel Prize winner for the chemistry, but the problem is the massive amount of CO2 you're left with. You've got to do something with it. We will see that there's some groups develop ways of pumping it underground, but another way is to convert it into something useful that the world needs 42 billion tons of. And one of those things is rock or sand or concrete. And this company in Los Gatos has generated, by a side reaction involving calcium oxide, it takes the carbon dioxide and converts it into these nodules of artificial limestone. Next slide. And one of the prime uses of that is in concrete aggregate. So you put the limestone nodules into concrete, as this chap is showing us, and it can be up to 44% of carbon dioxide from the air can produce a concrete aggregate like this, which is a very solid material. And to show that it works, they used it to actually put a new roof on a terminal in San Francisco airport. So it works. And this is a very promising method, because it's one of the few things that the world needs 42 billion tons of, is sand, because you grind it into sand, or rock, or concrete. So that's a method. The company's called Blue Planet, and I think they have some support from Leonardo DiCaprio. They certainly have a lot of financial support coming along. Then another approach, which is a company called Climeworks, which is based in Switzerland. They simply pump the CO2, having taken it out of the atmosphere, they simply pump it down into huge caverns underground. And the part of the world that has huge caverns underground is Iceland. So what they do is tack the carbon plant onto an existing geothermal power plant. They use the geothermal energy to power the system, because one of the problems with DAC is you need a lot of energy. So obviously, and you don't want to use fossil fuels to do this, otherwise it's pointless. So you have to find energy sources which are renewable. And the plant in the US uses solar energy. This one uses geothermal energy, and the carbon dioxide that it produces is pumped down underground into huge caverns that are a geological product of the volcanic nature of Iceland. So that is why they set up in Iceland, although they're Swiss. Next slide. They set up a small plant in Italy, and I wanted to mention this because I'm in Italy at the moment, and an association with the Turin Polytechnic, which is the place I'm working at. And it does the same thing, but with the side reaction, instead of producing rock, it produces hydrocarbons, in fact, hydrocarbons that you can burn. And it seems a bit silly to do that, but in fact, if you burn them as aircraft fuel, then you're saving the use of fossil fuels, and you're using hydrocarbons removed from the atmosphere. Next slide. So that's also been done on a larger scale by a plant in Canada called Carbon Engineering. Next slide. Yeah, and this does the same thing. It takes carbon dioxide out of the atmosphere, in this case using hydroelectric power, because it's up in the Rocky Mountains. And it turns again, using this side reaction, produces fuels. And the idea is to produce diesel, gasoline, and jet, so that the atmosphere itself is producing the fuel, not fossils. Next slide, please. Here's a couple of pictures of this carbon engineering setup. And this is they're building a gigantic set of blowers. This is just the first panel. So it's going to be a huge multiple of this number of blowers, which you need. So this is the beginning of doing large-scale air capture. I should mention a more natural method, because people seem to prefer natural methods, but my fear is that we have to go to engineering methods because of the huge amount of carbon dioxide we have to deal with. But a natural method that works is called biochar production, and this is a company there's many people doing this, but this is a company in Camarillo, California, in which you use a raw material which is organic, in a waste product. In this case, is pistachio nuts from this is a rural agricultural area. They use pistachio nut shells, next one, and put them in a sort of digester, which is a process called pyrolysis, where they're heated up under reduced oxygen content. And this turns them, instead of burning them, it turns them into a kind of charcoal-like material called biochar, an oil and a gas. And the gas is actually a source of energy. So it takes carbon dioxide out of the air. It takes carbon out of the pistachio nuts, which originally went into the pistachio nut from the air. So it's taken carbon dioxide out of the Earth's energy system. It's producing renewable energy and biochar, which is a useful agricultural material. And as a test case, they've got their university nearby is in Ventura, and the power plant for that university has got a biochar attachment, and it's generating biochar and energy as well. So this is the first university powered by pistachio nuts, so it shows what can be achieved. Next slide. So here we are with the problems, of course, is that it's been calculated that what we do when we add carbon dioxide to the atmosphere is damage the atmosphere, damage the climate, damage the planet at a rate of about $40 worth of damage per ton of carbon dioxide. So if we can take carbon dioxide out of the air at less than $40 a ton, we're gaining. We should do this everywhere and pay for it by taxation or whatever, but we need to do it. But if it's more than $40 a ton, then it's not economically worthwhile. In fact, that $40 is really a low estimate, so it really is worthwhile at more than 40, but we're only down to about 100 so far with the various. This is one of the companies involved. But remember what happened with solar energy. Solar energy now costs about 1% of what it cost a few years ago. In other words, if you apply engineering skill and money to a process, you can make that process cheaper and cheaper. And we hope that that's what will be possible with direct air capture. Once we start to spend enough money on it, the way we spent money on solar energy. Next slide. And also, of course, the quantities at the moment are too small. The companies are just starting up and are producing maybe tens of thousands of tons a year. What we need is billions of tons. We need thousands of these plants. It needs to be the biggest engineering project in human history if it's going to save us. Next slide. Two foundations which are helping to support this kind of work is the Foundation for Climate Restoration, which is in California, and the Climate Repair Centre, which is in Cambridge. But I see from what your organisation is doing that you're also busy in this very same field. So there are many more foundations that are devoting their energy to climate restoration and removal of CO2, because people are recognizing more and more that this is the only answer, that CO2 emission reduction is not the answer. Next slide. And this is just to say that this doesn't just affect humans, it affects the entire animal kingdom as well. And I'll just end with an advertisement now for an organisation which is intended for teachers who are interested in the effect of climate change in the polar regions and want to be able to teach and spread knowledge about the importance of climate change. So here's a web site that you can go to if you're interested in helping this organisation. So what I've said really is we have to take carbon dioxide out of the atmosphere if we want to save the planet from disastrous climate change. We can, up to a point, emission reduction will help because then it reduces the amount we have to take out of the atmosphere. But we're still left with a lot to take out of the atmosphere. And there are ways of doing it, but a lot of money needs to be spent on developing them. Thank you very much.
Thank you for the wonderful talk and scary as well. Now we have got 3 questions. We have passed the time, but still we'll go over those questions. They are very important questions, so we'll go a few more minutes to answer those questions. So first question comes from Robert Tulip. His question is, Arctic summer ice volume collapsed between 2001 and 2012 by 70%, from 12 to 4,000 cubic kilometers. If continued, that trend would have resulted in a zero ice volume by 2016. But from 2013 and 14, the ice minimum increased by 3,000 cubic kilometers. How visible was it in 2012 we assume the decade collapse trend at that time would continue. What is your current thinking on the likely timing for a blue planet event in the Arctic?
Well, first of all, there was a very, very strong trend. So it would have been very reasonable to continue to extrapolate that trend. And nothing that we know of happened to stop that trend. So it's still a kind of mystery. But one trend that has continued is the actual year-round average volume of ice. So the summer minimum has sort of hung itself up, and there's still ice there in the summer. But if you take the year as a whole and you average the ice volume through every month of the year, then there's a continued rapid decrease. And I think I showed us a slide of the reduction of volume. And so that what's taken over from simply the midsummer value going down to zero, which is what looked like it was happening, is that the midsummer value is hovering up and still existing, but the overall average ice thickness, average ice volume through the year has continued to decrease very rapidly. So I would still expect the sea ice in midsummer to go to zero before very long. But I think the bigger trend that is definitely not changing is the reduction of volume averaged over the entire year.
Okay, thank you, Dr. Wadhams. Let us go to next question, which is from Rituraj Fukan. He has two questions. Will the availability of technology of carbon dioxide removal be counterproductive, especially in the initial years when the technology is made available to countries, leading to increased mining for fossil fuels and destruction of nature by developing countries? And number two, do you see CO2 removal as the last inevitable resort to survive this existential crisis for humans?
Yes, well, to the first question, I'd say yes, there are potentially risks. And so far, of course, people have pointed to the risks, so much to the risks that they haven't done anything to actually bring about the reduction. I mean, the case where I think risks have been most studied has been geoengineering, which is this marine cloud brightening and firing up aerosols into the stratosphere. Now, I think that is risky because aerosols in the stratosphere stay in the stratosphere for quite a while, and you can't do anything, you can't steer them anywhere. You have to take what they offer, and what they offer might be changing the monsoon or something. It could be a serious side effect that you don't expect. So I think you have to be careful with geoengineering, but I think carbon dioxide removal shouldn't pose any problems because all it's doing is taking us back towards where we were before we added more CO2. So we're moving back towards the climate, the industrial level. So that's I think there's less danger there than there is in geoengineering. And regarding whether this is the last resort, yes, it is. I mean, I fear that it is, because having looked at the Paris Climate Agreement and the promises that haven't been kept by all the nations to reduce their carbon emissions, the fact that the CO2 level in the atmosphere is still accelerating upwards. It hasn't shown any sign whatever of flattening off. The population of the world is increasing, and the people in the world are getting more affluent. They will all want to imitate the Western lifestyle. They'll all want more cars. They'll all want bigger cars. There's a pressure which is, I think, irresistible to increase emissions. So even though we say and promise we're going to reduce our emissions, we actually aren't. And there'll be a huge reckoning and a huge disillusion very soon when people see that for all our supposed efforts, the CO2 level in the atmosphere is not coming down. So that's where the only answer then has to be removing the CO2 chemically, and that will do the job. But of course, the cost will be pretty huge. We have to be prepared to pay that cost.
Our next questions, and in the interest of time, the last question is from Bhaskar Malimadgula. Sorry about if I mispronounced the name. What do you think of growing diatom algae in oceans as a solution to sequester carbon?
Yes, actually, that is another method that I didn't mention, and I should have done. There was a whole set of possible ocean-based methods for reducing carbon dioxide. None of them have been developed to the point where we really can be sure that they work properly. But plankton is one. Another one is seaweed, growing seaweed on submerged mats and making use of the fact that seaweed can utilize sunlight and produce biomass. And another method is fertilizing the ocean with iron, which increases the production of plankton and the fish. So there's a whole set of ocean-based methods that some of them show a lot of promise, but I didn't, for the sake of time, I didn't get to mention any of them. But I think we should be aware of them. And in fact, there's a new alliance for ocean-based climate restoration just being founded this week, I think, by the Foundation for Climate Restoration, and is aiming to bring together organisations, which could include your organisation, that has an interest in ocean-based methods for removing CO2.
Maybe that will be our next topic, ocean-based climate restoration. That's an interesting topic to talk about. Thank you. We will conclude with a vote of thanks from Chandan Bhattacharya, and we'll make the recording available in our Facebook, and if anybody wants the link, we'll provide the link as well. And again, if you want to become a member and be active in this organization and in the climate restoration, please contact Mr. Chandan Bhattacharya at ckbhattacharya1963@gmail.com. Now we conclude and hear a vote of thanks from Chandan Bhattacharya.
Hi, my respected distinguished speakers, honorable viewers, dear interns and students, a very good evening to everyone. I am Chandan Kumar Bhattacharya. In our recent consecutive events in the webinar, today once again, it is my proud privilege to propose vote of thanks on behalf of Healthy Climate Initiative Group in the special occasion to Professor Dr. Peter Wadhams, Professor of Ocean Physics and Head of the Polar Ocean Physics Group in the Department of Applied Mathematics and Theoretical Physics, University of Cambridge. I take this opportunity to express our gratitude to the eminent speaker, Dr. Peter Wadhams. He is the UK's most experienced sea ice scientist with 40 years long experience in research in the sea ice and ocean processes in the Arctic and Antarctic. We are really proud to have you with us in this audience. We have learned from you about many facts and figures from your research and that are being investigated to achieve in this reduction of CO2 emissions that will slow down the rate of global warming. We will remain deep in debt to you for sharing number of informations and ideas to our viewers today. We hope to see you again in our program with more progress in the healthy climate movement. I have been very impressed and touched from the warm-hearted participation of people from all over the world in this online program, and for that, they deserve a big round of applause. On behalf of HCI, let me express my sincere thanks to the President HCI, Dr. Soumitra Das, for his constant initiative to conduct such event with the idea of generating awareness in the mass and upholding Healthy Climate Initiative's mission in cooperation with all active members and participants. At the same time, let us pray to the Almighty for fast recovery from illness of one of our very active members, Mr. Shudin Nondi, and take his active participation on his role in the HCI within short time. Thank you once again for your active participation to encourage HCI Group to hold this program online. Namaskar.
Thank you everyone. Thank you, Dr. Wadhams, and we'll see you again. Thank you.
Thank you. Thank you very
And
much.
here we conclude the program. Bye-bye now.